Hi, this is Physics 1, Chapter 14, Part 2. We're dealing with heat. And we left off, we did an example of a heat exchange. And so now we're going to do another example, kind of a refresher too from last video. Remember, the change in Q equals the mass times specific heat times change in temperature. Okay, so we're going to take H2O, and we're going to have a mass of H2O as 100 grams, and it will go from 25 degrees, so that'll be its initial temperature, and you'll have copper, and that will have a mass. Copper will be 82.35 grams, and it's going to start at temperature of 8 degrees Celsius. And it's going to be a closed system, and we want to know what is the heat transfer for the water and for the copper. If they come into equilibrium temperature at 29 degrees. So the final temperature is 29 degrees. Right, so the change in temperature for the copper is going to be a negative 51 degrees. And the change in temperature for the water is going to be a positive 4 degrees. So this is going to gain energy, this is going to lose energy. Now, the copper, the water has a specific heat. I'm using H for mass, so for the H2O, so put a little H's there. The copper is, the H2O is 4,200 joules per kilogram Celsius, and then the copper is 400 joules per kilogram Celsius. The reason I'm using this is what I have down, and you may look up a table and see this in this unit and just decide go with it, and you just gotta make sure that your units are right. So because we're going with something that has kilograms, I'm going to switch these to kilograms. So 0.1 kilograms, and this is going to be 0.08235 kilograms. Okay, so our change in heat for our H2O is 0.1 times 4,200 times 4. So 4,200 times 0.1 times 4. And you get 1680. Change in heat, the copper is going to be, the mass is 0.08235 times 400. And this was joules, since that was joules, times 400 times a negative 51. Okay, so you end up with a negative number because this is negative, these are not. I'm not going to put the negative in because I have it written. And you get something very close to what we have. 1679.94. So most likely this 29 may have been a little bit off from what the actual temperature would be. It'd be like 29.001 or something like that to make it perfectly even. So that's just a little rounding error. Right, so oops. So next thing is dealing with latent heat. And so every element, including water, has the same graph, but the temperatures may be different. Okay, and that's this graph right here. I'm going to draw it over here, draw it bigger too. And that is that there's going to be temperature A and temperature B. And this is T1, and this will be T2. And between this point and this A could be all the way down as far as you can go, in a sense. But at this point, the element is solid. It could be something like copper. It could be iron. It could be water. If it's water, we know what this temperature is. That's going to be 0 degrees Celsius. If it's something like iron, this temperature is going to be something different. And this is your melting point. Okay, so this is the MP melting point. This is energy being added. So as you add energy, it increases the temperature until you hit to that melting point. Then you have a plateau. And there's this latent heat. And this one will be latent heat of fusion. As this solid has to melt. And so you have so much time, it's going to remain at the specific temperature until it all melts. Then you get to point C. And between point C and point D, you have liquid phase. Okay, so point D is going to be a boiling point, which I'll call this MP, BP. So this will be 100 degrees Celsius if it was water. At that point, along this liquid phase, as you add energy or heat, you add, the liquid increases in temperature. Once it gets to this point, it's going to use the energy to break the bonds on the surface and stop becoming a gas. And so it gets to point E and it becomes a gas. At this point right here, that's the latent heat of vaporization. Okay. These 3 points here all deal with the same formula. This is Q equals mc delta T. Q equals mc delta T. And Q equals mc delta T. Okay, delta T is just the temperature change. This is just the mass. The biggest difference between these three is the specific heat. If you notice before, specific heat of ice is different than water, which is different than steam. So that's what's going to change these values. So you can't just multiply it by 3. These points here deal with a different equation. This is that Q equals mLF and Q equals mLV. So this is the amount of energy required to change a unit of mass from solid to liquid. And it is using the energy instead of raising the temperature to overcome the bonds and break the bonds and overcome the attractive forces of the molecules. This one uses the energy to allow the molecules to escape the liquid. Okay, these LF and LV can be found in in some table, and usually it always gives the melting point. So it gives these 2 temperatures here. These temperatures, a temperature down here or a temperature up here is going to be kind of arbitrary depending on how hot you're going to heat the gas or how cold was the ice or something like that. Right? So this is actually a very simple equation, and it only gives the Lagrange fusion and the heat of vaporization as positive numbers. Now, if we were going backwards in this, and we were going from a gas to a liquid, these LV and LF would be negative. And so if I wanted the total heat, so let's say I wanted total heat, total energy to go from T1 to T2, and let's say T1 is going to be at point A, T2 is going to be here, we'll call it F, and the way we would do this would be, we would do M for the substance, C for the solid, I'll do a little S for solid, and I'll go from T1 to MP, so it'll be MP minus T1. Notice this is higher than that, so you're going to end up with a positive number, plus the mass times LF plus the mass times the C as a liquid times your change in temperature. This is BP minus MP, the boiling point minus the melting point, plus the mass times LV plus the mass times C as a gas. This will be T2 minus the boiling point. So T2 is higher, so this is going to be positive. All of these are going to come out to be a positive number, and so you'll end up adding them together and you get a positive Q. Now in reverse, everything pretty much stays the same except we're going backwards. So we're going to start with T2. So this will be mass times the specific heat as a gas, and your final temperature is going to be your boiling point, so it'll be BP minus T2. That's going to make this negative, minus the mass times LF. You can think of this LF as negative, or you're just subtracting it. Right? Or we can do plus LF, but LF would be negative, so I'm just going to put the minus sign there. Then plus mass times specific heat as a liquid, and then melting point minus the boiling point. That's going to make this negative overall. So this will be negative, this is negative, this will be negative, minus mass times the heat of fusion, and then plus mass, C as a solid, and then T1 minus melting point. And this is going to be negative since the melting point is higher than T1. So all of these will be negative. You will end up with Q equaling some negative value. I'll just put a number symbol. Okay, so that's how this would work. Okay, so we want to, you know what, let me scroll up so I can see that table. But you guys can see the table too. Right, so we want to find the energy added to evaporate 500 grams of tungsten at the boiling point. So we're at the boiling point, so we're not changing heat. So this is just asking for the energy to evaporate. So the energy to evaporate, I put V there for that. It's going to be mass times Latin heat of vaporization. 500 grams is the mass. Latin heat vaporization for tungsten. We'll find tungsten. What will be Latin heat vaporization? You do kilograms per kilojoules per kilogram. So 4,800 kilojoules per kilogram. Oh, let me make that. Kilojoules. Alright, so we could change this to kilograms. That wouldn't be too hard. It would become 0.5, then 4800, and you end up with kilojoules. So that'd be 2400 kilojoules. Keep putting kilograms. Kilojoules. Right, the next one, we want to calculate the energy added to melt 500 grams of tungsten. So this is a Q of fusion, and it'd be mass times Langmuir fusion. Right, now we're melting this and we're evaporating this. So we went from liquid to gas, so it should be positive. We're going from solid to liquid, so it'll be positive. I just want to make sure of that. So 500 grams. The line heat of fusion for tungsten is 184. And this is kilojoules per kilogram. So we got to switch that to kilograms. And this comes out to be 92 kilojoules. Right, now we want to calculate the energy released for 500 grams of tungsten to condensate as boiling point. So now we're looking for condensation. I'll do a little C, so to label that. That'll be mass times the Langmuir fusion. Okay, I'm going to just skip the mass and put it to 0.5. Fusion, I'm sorry, vaporization. Just going to be a negative 4800. So this would be a negative 2400 kilojoules. Basically, that negative means it's being released. Right, same thing for the next one. This is going to be freezing. So FR. And it'll be the mass times Langmuir fusion. So 0.5 times the negative 184. So it'll be negative 92 kilojoules. Okay. Alright, so now we're going to add everything together. And it's a multi-step problem. Alright, so you have an 10-gram ice cube, and it is taken from the freezer. So this ice cube has a mass of 10 grams. It has a temperature, I'm going to call it temperature initial, of negative 15 degrees Celsius. Has a melting point, since it's ice, of 0 degrees Celsius. Has a boiling point of 100 degrees Celsius. We may not even get to that. I don't think we do, but I'm just having it there for now. It's placed in a closed box. So this is the box. And we put the ice cube in it. And that closed box has a temperature that is 20 degrees Celsius. So I'm going to call that T2. And the ice cube melts into water and eventually will reach the final temperature of 17 degrees Celsius. Right. So what is happening here is none of the masses particles will escape. Some particles from the air will go into the ice and all that, but it's not going to ever leave the system. We want to know how much heat is added to the ice, basically. So way we're going to do this is we're going to kind of track this ice. So the ice will go from negative 15 degrees to 0 degrees. So that's going to be a change in temperature. Okay, we could just write it as kind of 15, but I'm writing it out so you see how it becomes positive. And the mass is equal to 10 grams. And specific heat, let me write that down. Specific heat of ice, 2.1 joules per gram Celsius. Right, so we have grams for mass, grams for specific heat. So we're going to do 10 times 2.1. And so we get, that's the first part. Then it's going to melt at 0 degrees. So that melting line here, fusion, we need. And for ice, it's 333. And here I want to show you a little trick. Kilojoules per kilogram, which is also 333 joules per gram. Right. That's the nice thing. If you just convert them both, the number doesn't change because you're multiplying by 1,000 and dividing by 1,000. So this mass in grams would be 10 grams times 333 joules per gram. So we'll have joules for both of these. And so what we get here, actually I'm going to do it down here. Actually, might as well just do it in a calculator. So 10 times 2.1 times 15 plus, I'm just going to multiply that by 10 to make it a lot easier. So we get 3645. So 3645. That's to bring it up to 0. Now I could have added this with the third part. I actually forgot, but we're only at 0 degrees. We gotta go up to 17. That's where it reaches. So I'll add this number to that. So our total heat change in the ice is going to be the 3645 plus now our change to go from for the liquid to increase to 17 degrees. So that's going to be a mass of 10. Water is 4.2 joules per gram Celsius. And then the temperature is going to be 17 minus 0. Okay, so plus 10 times 4.2 times 17. And we get, oh, I added it twice. So don't worry about that bottom number, 4359. Right, so that's the total heat to increase this ice from negative 15 to 0, to melt it, and then to increase the water from 0 to 17. Right, so this part here is the total heat added at the bottom from the air to the closed box. This is what the from the air of the closed box to the ice. So this is what the ice has to get from the air. So this air is losing, this change in energy for the air is a negative 4359. And that's going to be equal to its mass times specific heat of air times the change in temperature. Well, we don't know the mass. We do know a change in temperature. So negative 4359 equals the mass. Specific heat of air is 1.01 joules per gram Celsius. And we have our energy in joules here, so that's fine. This means our mass is going to be in grams. And so change in temperature goes from 17 minus 20. So it goes from 20 to 17. So you get negative 3 on this side. Alright, these two negatives will cancel out. So mass is 4359 over 1.01 times 3. And we can find the mass of the air. So 4359 divided by 1.01 and divided by 3. 1438.6 grams. Oops. I don't know why I put another equal sign. Alright. So that's a multi-step. We can have the step go as far as going to a gas, even. All we need to do is have the information for it. Alright, so next things I want to kind of mention are what's called transfer mechanisms. You may have heard of most of these. Some you may have an idea about what they are. Before I get into this, let me check the time. Okay, I have enough time to probably finish this actually. Alright, so there's actually three: conduction, convection, and radiation. I'm going to start with conduction. This is the transfer of heat by molecular electron collisions within a substance. Right, and so main thing for this is think about touching. Right, two things have to be touching to have conduction. And so let me kind of draw an example. Actually, if I have I'll draw an example up here. Let's say you have a rod and at the end is a Bunsen burner that has a flame. I don't know how to draw a flame that well, but you know what? I know how to draw it. That's some red. That's some yellow. Okay, that's the flame. And someone's going to be holding it on this end. Okay. And so we have a certain length here, from here to here, of while they are holding it, to when they start to feel the heat. You're going to have a certain area here that's within the flame. I mean, if this flame was big enough that the whole thing is engulfed, well, that's a pretty big area. You're going to have a big energy flow. We have a constant K. This is another K. This is based on thermal conductivity. It's a characteristic of the material. So let's say this was steel, and we are 1.1 times 10 to the negative 2. No. That's calories. I'm not dealing with calories. 40. A lot easier, see? 40 joules per second per meter per Celsius. This is actually telling you units that you're going to have. And then you have a temperature change. This is going to be T1, T2. Okay, so Jamie's. Hold on a second. Yeah, that's right. T1, T2. Okay. Let's see. I got mentioned the length, mentioned the temperatures, mentioned the area, mentioned our K. The Q over T, this is basically heat flow. Okay, this is how much heat over time. Okay, so it's heat per time. Okay, and so this QT equals KA T1 minus T2 over L. So let's say this is, I don't know, 0.5 meters, so about 50 centimeters. This is heated at 200, no, that's too high, 60 degrees. And this is just at 20 degrees. And then this area, let's say, is just pi times 0.1, so it's 1 centimeter squared for the 1 centimeter in radius, so about 2 centimeters in diameter. Right, so your heat flow would be 40 times pi times 0.1 squared, that's your area, times T1 minus T2, which would be 40 degrees. That's T1 minus T2, and then 0.5. Right, so if we calculate this, $40 times pi times 0.1 squared times 40 divided by 0.5, so 1 times by 2. You get a heat flow of 100.53 joules per second. Which, notice that's a unit of watts, so it's a unit of power, joules per second. Alright, so we'll do one more. We have 56 centimeter long copper rod. So L, let me list out this stuff first. L is 0.56. Radius is 2 centimeters. So R is 0.02. I made that 10 centimeters actually. Oh well. Okay, so this 10 centimeter radius up here. T1 is 460 degrees. And we're going to immerse the other side in water, so that would be T2 would be 22 degrees. Now, the hotter side is always on this side. That's the way the heat is flowing, so that you have a heat flow going towards the cold side. So this is always high minus low. And then, let's see, we have copper, so K is 380. Right, so Q over T is 380 times pi times 0.02 squared times 460 minus 22 over 0.56. So 380 times pi times 0.02 squared times 460, I'll put this in parentheses, minus 22. Let me just do this one first. And then we divide it by 0.56. And you get 373.5 joules per second. Right, so this is conduction. Convection deals with liquids most of the time, or gases and liquids and anything that moves, flows. And so the transfer of heat in a gas or a liquid by means of current or heated fluid. So the fluid moves and it carries energy with it. So as you heat up this bottom, remember heated water will rise to the top. So this water rises up. Well, this cold water then has nowhere else to go but down, so it rises down. But then that cold water heats up, and this hot water up here that has just gotten up there starts to cool. So then it comes down and that cold water moves back up, and so it just gets a circulation going through as the water gets heated. And so we see this not just in heated liquids, but we see this in heated smoke. It will reach and go up until you reach that area where it has the same density, and then you see it kind of flatten out. So convection occurs whenever fluids and gases are subject to a temperature difference. So cold air on top, hot air on the bottom. Right, now, before I move on to radiation, when the Pilgrims came over from England, they assumed that New England, Connecticut, Rhode Island, Maine, they were going to be warmer because they were in towards the south. And they had to travel south to get there. Well, they found out in a very bad way that New England actually is colder than England. And the reason is with a current. So I'm going to do my best and try to draw a little bit of the United States. You have Florida, and it comes up. And so you have New England up here. Florida down here. And you have England all the way over here, but higher. Well, we have a current that goes like this. So it brings this hot water up to England, and it warms England. We don't have that over here. So New England is actually colder, even though it's farther south than England, because of this current. If I remember right, I want to call it the North Atlantic current, which they talk about in the movie Day After Tomorrow. I'm pretty sure that's the current. That's the name for it. But that's how currents will transfer energy. Now, big question is why there exists that current. That I'm not sure about. Never really looked into that. Probably has to do with the shape of the earth and all that. Anyways. The last thing is radiation. And I think this is the last thing. Yep, pretty much. Alright, so Actually, I do have one example. Well, it deals with radiation. I think I have it listed as conduction though. I don't know why. Alright, so radiation is the transfer of energy by means of electric magnetic waves. So basically, you have the sun. Sun shines light down in the form of electric. Oh my god. Trying to go quick here. Electric magnetic waves onto the earth. And so our flow rate for this is equal to E, and this is not the exponential E. I'll get into what this is. E sigma A T to the fourth. The sigma is a constant, and it's a Stefan-Boltzmann constant of 5.67 times 10 to the negative 8 watts per meter squared Kelvin fourth. For the sun, this constant times that temperature of the fourth. Sun's about 6,000 degrees in temperature. For the sun, that is treated as constant, probably because it comes up because it is the closest energy source, as 1,000 meters squared. So if you know your energy source is the sun, you can kind of skip all that math with this being 1,000. Right, this E is basically depending on the color of the surface or the kind of material itself in a sense. So black surfaces absorb heat, and so they have a value close to 1. Reflective surfaces have a value very close to 0. If it's more dark, it's going to have a higher value. If it's more reflective, it's going to have a 0 value. So since we're multiplying this, if it's really close to 1, it's going to have a higher value. So darker surfaces will have more heat flow to them. And if it's really close to 0, it's going to have a really small value. So reflective surfaces is actually reflecting away a lot of the heat. And then the heat flow also depends on the area. This is the surface area of the object and the path of the radiation. So this we're going to see here soon. It depends on the path. So if you're at an angle, the area can change. The larger the area is exposed, the higher the heat flow. And then the temperature. More temperature, higher the heat flow. The temperature is one of the biggest things since it's to the 4th power. When you're at an angle, we can see from this triangle, this is your area exposed to the sun, but the sun's coming down at an angle. So this is actually what's in the path of the sun. So you actually have an area cosine your angle. Right? So this is your A is actually your hypotenuse here. And so this is your adjacent to that angle. That's why you use cosine. So this can break down as all the way with the sun coming down as 1000 E A cosine your angle. Alright, so let's do this last example. Let me check the time before I do this. Okay, a little longer this video, but we'll get this done and then you'll be in the last chapter. Alright, so we want to know how long does it take the sun to melt a block of ice at 0 degrees Celsius with a flat horizontal area that's 1 meter squared and a thickness of 1 centimeter. We'll assume the sun's rays make an angle of 35 degrees with the vertical, and that the emittivity of ice is 0.05. Alright, so E equals 0.05. The angle equals 35 degrees. The area we're looking at since we don't have a hold on a second, let me just see how I want to do this. We'll have to find the area through, we're giving them, let me see here. We want to find that time, so that's what we're solving for. Oh, I see, right, okay. I'm looking at, for some reason I need a volume. Our area is going to be the point, the 1 meter cubed. Oh, I'm sorry, 1 meter squared. All right, and then let's see, what else do we have? We have the thickness of 1 centimeter. So that's right, thickness 0.01. And let's see. So let's get into our delta Q. We have delta Q over T equals E sigma A T to the 4th cosine theta. Remember, sigma T to the 4th for the sun is 1,000. So this becomes 1,000 E A cosine theta equals delta Q over T. But we're solving for T. So T equals delta Q over 1,000 E A cosine theta. This delta Q is going to be the mass times specific heat of dealing with ice, right? Yes, ice times our change in temperature over 1,000 E. I'm sorry, I'm using the wrong thing. We don't have a change in temperature. We're at 1 temperature. It's going to be the mass times that heat of fusion over 1,000 E A cosine of the angle. Okay. Now, we weren't given a mass. Mass, though, is equal to density times volume. Our density of water is 917 kilograms per meter cubed. And our volume is the 1 meter squared times the 0.01 thickness. Right, so this is moving on me. Okay. So the mass is equal to 917 times 1 times 0.01. 9.17. Right, so this time, this temperature, or I'm sorry, yeah, the time is 9.17 mass. We're dealing with water, so specific heat of fusion is 333 kilojoules per kilogram. This mass was in kilograms. we're going to have to switch this though to joules per kilograms. So this is 333,000 joules per kilogram. So 33. Alright. This is 1,000. This is 0.05. The A is going to be 1, which, I mean, I can write it, but I won't calculate it. And then cosine 35. Yeah, 35. Alright, so 9.17 times 333,000 divided by 1,000 divided by 0.05 divided by 1, same thing, divided by cosine 35. And how does that happen? I'm in radians. Alright, so let's do this. Go up to this step here before I divided it. Now divide by cosine 35. There you go. So time is 74,555.4 seconds. Right, which is about, if you want to figure this out, let me make sure. I don't know. I just want to make sure about this. Right, so that's how many seconds. There is 60 seconds in a minute. So that's how many minutes. 60 minutes in an hour. So that's how many hours. So yeah, 20.7 hours. So 20.7 hours. Okay, so not even a day. And we're assuming the sun's out for that long too. Okay, so must be on a really, really short day. Or a short night, I guess you can say. Alright, so it's 52 minutes. That's kind of long, but we got one more chapter after this. The next chapter will probably be broken up into a lot of different videos because it's a pretty long chapter. But it is the last chapter. I'm looking at the pages right now. I got about, looks like 12 pages. This was about 10, but there was a lot of material in the next chapter. Alright, I'll see you in the last chapter.